Okay, let me review what I have covered last time. I talked about types of convergences in distribution, which is most weakest form of distribution, convergence of random variables. We say a random variable xn converges to x as n goes to infinity in distribution if the distribution converges. And we also talked about convergence in probability. We say that xn converges to x in probability as n goes to infinity if for any epsilon greater than 0, the probability of deviation set in this deviation set, basically xn deviates from x larger than epsilon, right? So deviation is greater than epsilon. Probability of such a set goes to 0 as n goes to infinite. Okay, and then we also talked about almost sure sense convergence, or almost everywhere sense, or with the probability 1 sense. Okay, that is the case when xn converges to x almost sure as n goes to infinity if probability of omega limit of xn is equal to x. So collection of all those omega. So set of omega that xn converges to x. Okay, random variable. The map actually, random variable is a map, and the map actually converges to x. Or you can say the same thing with this expression for any epsilon greater than 0, probability of this set where xn deviates from x infinitely often, right? Then is the probability of such a set is equal to 0. Then we say that it is almost sure sense convergence. Okay, and I have given one more definition which appears in the next page, right here, almost sure sense convergence on another one. So those are the type of convergences. And then one thing that I wanted to mention is that is this, okay, let's see. Okay, in probability, we can change this inequality to this way. Then this probability of a set that this deviation is smaller than or equal to epsilon, the probability of such a set goes to 1. Okay, so we can I can say convergence in probability in this manner. So if I say it one more time, for any epsilon greater than 0, probability of this set x omega xn omega and x omega smaller than or equal to epsilon, this probability goes to 1 as n goes to infinity. That is equivalent to say that xn converges to x in probability. So these two statements are equivalent. Okay. The same is true for almost sure sense expression. So for example, in this expression, I can exchange with this, and then this exchange with 1.0. Okay, so probability of a set where xn converges to x is equal to 1.0. Okay, and then same thing is also true for the other expression given in the next page. For example, this one, instead of deviation greater than this, I can also say that deviation is smaller than or equal to epsilon, then the probability of such set is equal to 0 as we take the limit. Okay. So those are different types of, different ways of the same sentence, same statement, okay, same statement we can have for each convergence type. Okay. Let me clear this up. And so I talked about convergence in probability, convergence in almost a sure sense previously in previous page, and in this class we will use convergence in probability a lot, and a little bit on the convergence in almost a sure sense manner. Okay. So if I apply those type of convergences into the laws of large numbers, it means this. So weak law of large numbers, we let x1, x2, and so on to be IID with expectation of absolute value of x1 to be finite, and expectation of one of them is equal to u. Okay, as n goes to infinity, Sn, which is the summation of all of them, divided by number of addition n, this converges to mu in probability. So we can obtain these results in the improbability sense, and when we do that, it is called weak law of large numbers, and we say it's a strong law of large numbers if this ratio converges to u mu in almost a sure sense. Okay, so those two are laws of large numbers we have. Okay,